University of Helsinki, and in my postdoc at Lund University and at SMHI. Uh, huh. So most of my work deals with aerosol formation. And this is a plot I guess most of the aerosol scientists show to the rest of the people as to show our motivation as to why we want to work with aerosols. So this is the very popular figure from this IPCC, or this assessment report 6, I guess, which shows the changes in this effective radiative forcing from this pre-industrial 1750 to 2019. And as you can see, most of the components that the anthropogenic components and the stuff like carbon dioxide and the water vapor and all these things are having constituted this positive radiative forcing or heating up the planet. But then aerosols, along with land use, uh, constitutes this negative effective radiative forcing. That means it's kind of cooling the planet. And there are two main components of aerosols, which are two main ways they do it. It's by this aerosol radiation effect and the aerosol cloud effects. And what we do, or what we believe that we are trying to do, is trying to reduce this uncertainty here. This black line, this is the uncertainty in these aerosol processes, and we think and we hope that our work that we are doing is aimed towards reducing this kind of uncertainty in this effects of aerosols and how much they contribute to this effective radiative forcing. And why secondary aerosols? So this is again a model result from this assessment report 5, and where they show that these are the contribution of aerosols to radiative forcing. And as you can see, most of the aerosol effects, the secondary aerosols such as sulfates, nitrates, and secondary organic aerosols all have this kind of a negative radiative forcing here. Although there's this huge uncertainty, but the trend is mostly towards actually cooling the planet. Some of the examples from various studies have shown that like this dimethyl sulfides derived sulfates, and dimethyl sulfide is the biggest source of natural sulfates in the atmosphere, I guess. And the sulfates which are derived from this DMS, they contribute to the cooling, like a negative radiative effect. And for the aerosol radiation, the values are somewhere around 0.06 to 0.11 negative. And for the aerosol cloud interactions, various studies have reported various values, but it still somehow ranges between 0.19 to 0.76 watts per square meter. So you can see there's this huge range reported by different studies. And we are all probably trying to reduce this range to a more, to constrain this range to a more reasonable value, which can actually give us a better description of the impacts of these aerosols on the climate. Why polar regions? As everyone here is for this CAT seminar, I guess we are all familiar with the problems or the issues the polar regions are facing. But one of the major reasons is this polar amplification, or for example, the Arctic amplification, which is basically the increase in the warming of the Arctic regions compared to the global average. And the recent published paper in 2022 puts this number as almost 4 times the global average since 1979. Although this Arctic amplification is believed to be driven by the feedbacks between the snow, ice albedo, and the retreating cryosphere, and also the transport of latent heat and dry static energy from the mid latitudes, there's also a role that aerosols play. But the thing is, we are not really certain how aerosols impact the Arctic amplification. Does it dampen? Does it make it worse? Because we do not know a lot of things about how aerosols are produced and the sources of aerosols and the way these feedbacks work in the Arctic regions. So to give a brief example, this was this paper published in 2021 by Julia Scamale, and they looked at the aerosols in the Arctic. And since Arctic has a very low aerosol loading concentration, so most of the aerosols can actually act as this cloud condensation nuclei, and they form these low-level clouds in the Arctic. And they suggested that this aerosols in the Arctic, especially in the winter time, these low-level aerosols or these low-level clouds can actually cause a warming effect. So generally over the globe, it's believed to be a cooling effect, but at least in the winter time in the Arctic, aerosols can actually have a warming influence. So, and the recent Mosaic expedition, which was this 1-year ship icebreaker campaign, actually showed that the blowing snow in the winter time, it was from November to December, I believe, or October to December of 2019, they did these measurements and they found that the blowing snow can actually increase the cloud emissivity, the long wave cloud emissivity, and cause warming of the surface in the Arctic region. But in the summertime, the picture is completely different. In the summertime, you have these secondary aerosol formation, which is a dominant source of aerosols in the Arctic. And most of this is via this new particle formation. So basically, formation of these small sub-nanometer size clusters, which then grow in size to tens of nanometers or even hundreds of nanometers. And the thing is, in the Arctic, there are a lot of sources of these precursors gases, which can gases which such as sulfuric acid, ammonia, amines such as dimethylamine, trimethylamine, or other amines, iodic acid, MSA. There are a lot of sources of these, and we still do not know. We still have not marked on all the sources that can emit these kind of compounds. There's this nice schematic by Breen from this paper in 2023 where they looked at, we just show that you have this DMS emissions from the algae from the open water, then you have nitrate ammonia from the seabird colonies, from the sea, open sea as well. You have iodine from the inorganic sources and the organic sources such as methyl iodide, or this from the sea open water as well. And you have unaccounted organics. There have been a lot of research now towards understanding the organics in the Arctic region, and you have these melt ponds which can again emit some kind of combination of these compounds as well. So there are a lot of sources and a lot of precursor gases, but we still haven't basically figured out what these are completely. And to complicate matters further, the measurements also show that different areas in Arctic have different precursors which contribute to this new particle formation. So Lisa Beck, who was at Helsinki at this time, they did these measurements in Willem, which is considered to be high Arctic, and New Orleans, which is like 79 degrees south north, so beginning of Arctic region. And they did these measurements during springtime, and they found that in Willem, during when it's surrounded by sea ice in the springtime, iodic acid was driving the new particle formation. But then when you come down to New Orleans, it's sulfuric acid ammonia, this ion induced or ion mediated sulfuric acid ammonia, which drives new particle formation and secondary aerosol formation. So it's not only complicated by the amount of sources we know, but also complicated by the location of where these new particle formation events happen. So looking at all this, what we decided was to, because we are modelers, we decided, okay, let's try to do some modeling for the Arctic areas and see if our models can actually capture the secondary aerosol formation. So we consider two periods, one for the Arctic region and one for the Antarctic region. One was the spring and summer in these for these campaigns. So one campaign was in May 2018, led by Tropos. They did some unmanned aerial vehicle measurements at Mount Zeppelin and Gruber Badet. So we used that campaign from May 2018. We simulated that specific period, and then we went down, and then we also looked at some sites in the southern hemisphere and the Antarctic Peninsula at Abo and Neumayer, and we selected the year 2015 Jan and 2019 Jan. And the main aim of this study, these simulations, was to actually understand if we can actually the models can actually capture the formation of the secondary aerosols, and can we actually estimate how they are growing, like what's the reason why these particles grow in these marine polar regions. So to just illustrate, so we have the sites such as Mount Zeppelin here. We look at some air mass trajectories derived from flex part or high split or whatever you choose, and then we look at particle formation events and how they grow. And by the time they reach the station along these air mass trajectories, we look at our simulated results and compare with measurements and see how good our particle size distributions and gas phase concentrations are when we compare to the observed or compared to the observations at these sites. Yes. So how do we actually do it? So we have a kind of a pipeline right now. We use different models. We actually use 4 different models. One is called FlexPart, which I guess most of us are familiar with. It is AC/DC. I'll come back to that in a minute. And then this is this DMS multi-phase chemistry scheme, and I'll also come back why we use it. And we have this aerosol dynamics, gas phase chemistry, and radiative transfer model called ADChem. So all the results that I'm showing right now have actually been published already. There were a couple of papers from 2022, which we published when we looked at the secondary aerosol formation in Arctic. And then also we performed the simulations for Antarctic, and we published it this year. And also looking at how continental and marine air masses influence secondary aerosol formation in this kind of a boreal forest as well, like in Hutiala. So I'll just briefly go over the models. So FlexPart, as like I said, most of us are familiar with or have used it or are developing it in some aspect. It's basically just a Lagrangian particle dispersion model developed by Andreas Stoll and his group. What we use from FlexPart is air mass trajectories, these average air mass trajectories, and also residence time or potential emission sensitivities, which we can call it as residence time as well. So we use these emissions, we use emissions from ECARD, and we use the meteorology data from ERA5 along these FlexPath trajectories and read it as an input to the model. So we get the emissions along the trajectory. We have this kind of a nice, I would say, map of all these residence time. We get all the emissions and we use it as a cumulative emissions as an input to the model. And the meteorology is along these average trajectories. And next is AC/DC, which is the very popular band most of us listen to, but this is not the model that we use, unfortunately. But this is a very cool model called Atmospheric Cluster Dynamics Code. It's been in use for over a decade, I guess. And basically what this model does is it gives you a formation rate number by solving these birth-death equations of different clusters. So it uses inputs such as this molecular thermochemistry data, like of Gibbs energy or enthalpies, to calculate the evaporation rate of clusters. So to explain it simply, you have small clusters. Suppose, for example, sulfuric acid ammonia, you have the clusters forming, then you have a scavenging sink due to bigger particles or whatever, and then you give this as an input to the model, and in the end, it just spits out this kind of formation rate number, which you can call it as a new particle formation rate, and then you feed it to the bigger model, in this case, which is ATCHEM. So using this, we can actually consider new particle formation via different pathways, such as ion-mediated sulfuric acid ammonia, iodic acid, and some base such as DMA or iodous acid or sulfuric acid DMA. We can test all these different pathways and look at how they contribute to secondary reservoir formation together or separately. And then we also use this DMS multiphase chemistry scheme. So this was developed by my colleague at Lund, Robin. So basically, it's an updated version of all the DMS multiphase chemistry scheme. It just updates. It has some new reactions for the OH oxidation of DMS products, and then how they partition the gas phase, and how they react in either in the aqueous phase or in the gas phase, and how yeah. So we use this model basically to see if this aqueous phase chemistry, this DMS aqueous phase oxidation, is important for the growth of aerosol. So DMS aqueous phase oxidation can produce MSIA and then like MSA in the aqueous phase. So we wanted to see if in these marine low-level clouds, is the aqueous phase more important, plays a bigger role in the growth of particles in comparison to the gas phase MSA production by condensation. And the fourth and the final model is ATCHEM. So all these things we have, we put them into this model called ATCHEM. So basically, ATCHEM is a 1D column model. It has some like 40 different vertical layers. We run it along these average air mass trajectories generated by FlexPart. It takes into account the formation of clusters via AC/DC, primary emissions from ECARD or from CAMS, and then it uses vertical mixing. Then it kind of simulates the growth and the loss of these particles along the trajectory till it reaches the measurement station. So the first results are the results from the site from New Orleans in the Arctic region. So I'm just going to show the median particle size distributions here because it's much easier to show. And by the way, this is the median particle size distribution and not the mean. This is an error here, but it's much easier to illustrate that this way. So we considered two different sites, Gruvabad, which is basically at 67 meters, so considered the sea level site, and there's Zeppelin, which is at a mountain site. So as you can see in the median particle size distribution, the blue one is the Gruvabad particle size distribution. We are able to fairly simulate the particle size distribution when compared to measurements at the site. But at Zeppelin, we're not able to do that very well. I mean, there are different reasons why we are not able to do it at Zeppelin, because it's a mountainous site. A model cannot get the vertical mixing around this mountain slopes quite well and all. But at least at the ground side at Gruvabad, we are actually able to simulate a representative particle size distribution. And when we compare it with the gas phase concentration, so we only had data for the particle size distribution and the gas phase concentrations. And we can see that most of these are the median values. If you can see the median value for MSA, the model, the simulated and the measured values are around the same ballpark. Iodic acid we are underestimating in the model, and sulfuric acid is also quite okay. We know that why we are kind of underestimating iodic acid, because this was pre-Finkenzeller's research paper where he did some measurements at cloud, and he came up with two other reactions which actually boosted the iodic acid gas phase concentrations, but this work did not include this. So we kind of underestimating iodic acid also because we are missing some reactions. What Lisa Beck showed in her paper, or what they expected at Gruobadat, is that sulfuric acid and ammonia should be the driving mechanism for secondary aerosol formation. And in this work, we only use sulfuric acid ammonia. And as we can see at the station, when the median particle size distributions are in kind of sort of agreement with the observed values, we can see that, okay, sulfuric acid ammonia are probably enough to form the particles, but then the growth is something else. We form particles by sulfuric acid ammonia, but then there's some mechanism which grows the particles. So for growth, we do to see what is causing the growth, we do some more simulations. We did some more simulations. We did some simulations by actually checking, looking for in-cloud processing or aqueous phase chemistry, the impact of both of these. So one good result is that you have, in this base case, where we considered all in-cloud processing and aqueous phase, we can see this kind of Hopel minima, which is a distinct feature in some marine, most of the marine air masses. It's like a minimum here, which forms due to this non-precipitating cloud cycles. I guess a lot of you know this better than me here. But our model, at least in the base case, is actually able to get this kind of Hopel minima. It's shifted to a larger size range. That's because of the assumed supersaturation value. But yeah, we are getting it at least. So we are happy about that. But then we did some simulations with this without cloud, where we did not consider any in-cloud processes, but we considered aqueous phase chemistry. This is analogous to having a particle, a deliquescent particle, a particle with some water, but there's some aqueous phase chemistry going on, but there's no in-cloud processes. And we also did one which is called Woe dissolution, where we did not consider any cloud processes, so there was no irreversible aqueous phase chemistry going on. And as you can see in the particle size distributions, most of the particle for these different sensitivity tests, the particle size distributions are shifted to a larger size, which makes sense because if you have no in-cloud processes, you do not grow the Aitken mode sizes enough. So that's why most of the gas phase precursors such as sulfuric acid just condense onto the larger particles and just grow them and not the smaller particles. But when we take a look at what constitutes the particles, so here we can look at this base case plot and the Woe dissolution plot. This is just the relative mass fraction. The red is sulfate, and this is on the x-axis is your the size distribution. And for the small sub 10 nanometer particles, of course, sulfuric acid sulfates SO4 minus and NH4 plus, because it's just sulfuric acid ammonia particles. But as we go larger in size, we see that then it's sodium and chlorine, of course, because sea salt particles. But then there's MSA, which is actually contributing to the growth of particles. So as we come closer to like 20, 30 nanometers, MSA starts to contribute more and more. And once we cross the 100 nanometer threshold, MSA starts to contribute a larger fraction to the mass. But in the Woe dissolution case, where we do not have any aqueous phase chemistry, MSA is only formed in the gas phase and it's condensing onto the particles. So at least what we can see from here, and taking into account also the particle size distribution, because they only condense on the larger particles, the MSA condensation from the gas to the particles is not enough to grow the particles in the Aitken modes range, because MSA is a semi-volatile. So it logically, it of course condenses onto the larger particles. But then that's why to grow the smaller particles to these Aitken mode sizes, which is 20, 30 nanometers to maybe 50, 60 nanometers, you need the aqueous phase chemistry, and this MSA, which is formed in the particle phase through this MSIA oxidation, is very important. So the conclusion from this work, what we found was, aqueous phase formation of MSA, and then of course sulfuric acid is also condensing, is crucial to the growth of the particles. Then let's jump to the other hemisphere, the southern hemisphere. This is from the latest work where we did these simulations for Antarctica, and like I said, we selected two sites. One is Aboa, and the other was Neumayer. It's not clear from this figure, but Abo is a site which is inland, so it's like 130 kilometers inland, and Neumarkt is by the coast, maybe a few meters from a few tens of meters from the coast, like 20 or 30. So there was a measurement campaign at Aboa in 2015, and they published results, and they said that it was probably the secondary aerosol, the new particle formation, the secondary aerosol formation was governed by ion mediated sulfuric acid ammonia particle like clustering. So when we started doing the simulations, we actually wanted to see if actually ion induced sulfuric acid ammonia is actually enough to explain the growth of these secondary aerosols or not. So we also used, because we have ACDC, or now it's called clustering, we also had the option of using different clustering systems, such as now we use the tried and tested sulfuric acid ammonia, we have the sulfuric acid DMA, and we also have this neutral iodic acid and some bases, in this case, DMA and iodous acid. So we wanted to see if is it only ammonia sulfuric acid which can explain secondary aerosol formation, or maybe there's a role, or there's a universe in which iodic acid and also plays a role at forming these particles, and then that's what we measure at the station. So this is a simulation where we only use sulfuric acid ammonia and sulfuric acid DMA. DMA plays a smaller role in this. So as you can see here, this is the black is the observed and the colored lines are simulated. We are completely missing the Aitken mode particles at both Abo and Neumayer. So we are just completely missing it. That's probably because we have some particles which are being formed over the open ocean, and they grow to a larger size by the time they reach the station. So almost near the station, there are almost no particles being formed. So then we decided to see, okay, if we use some iodic acid system, does it actually improve the results? And then we first tested with the iodic acid DMA system, and we can see now we have this kind of a nucleation Aitken mode. It's not perfect, but okay, we have an Aitken mode of particles. That means there are some particles which are being formed a few days or one day before it reaches the station, and then they can grow by condensation of sulfuric acid or aqueous phase chemistry. And at Neumar, it's much better. So because Neumar is at the coast, you definitely should have some iodic acid or influence over there. So once we include this, we see that there's an improvement. At least we are able to capture this Aitken mode about, I would say, fairly okay. Yeah. But we did on other simulation where we used a different base, this iodic acid and iodous acid. And of course, we don't see the Aitken mode here, but we see we see an Aitken mode, but it's again shifted to the larger particle size. And at Neumar, again, the results are pretty acceptable. They're pretty good. We get this nice Aitken mode here. So then we thought, okay, so why are we missing these nucleation mode particles? To understand this, we can look at it in two ways. One, we can look at things that are happening along the trajectory and things that are happening close to the station or local processes or in the vicinity of the station. So yeah, this is a dense plot, but I'll try to explain it as easily as possible. So if you look at what's happening along the trajectory, these are just formation rates. Let's just focus on ARBOA for now. So this is sulfuric acid ammonia, this is iodic acid, iodous acid, and sulfuric acid DMA. These are the formation rates for all the for 4 days upwind of the trajectory. The round O symbols are when the air mass is over the land. The crosses represent formation rates when the air masses are over the ocean, and the diamonds are when the air masses are at the station. And the size represents how far it is away from the station. So the smaller size means it's closer to the station, and the larger size means it's away from the station. So for sulfuric acid ammonia, most of the air masses, so if you see the ocean air masses or the ocean, these crosses here, I mean, the formation rates are quite of logical. It's like 1 per cubic centimeter per second. But as you come on land, of course, it drops because you have very less ammonia or some precursor gases available. So your formation rates drop because there's less gas phase concentrations available. But for iodous acid, it's kind of important because for this iodic acid, iodous acid system, because here over the ocean, you have, further away from the station, you have kind of like very small formation rates. But then, I mean, below these red circles, trust me when I say below these red circles, there are again these crosses which show that at the ocean, there's this huge formation, like you're forming a lot of particles from this ammonia, from this iodic acid pathway. So what we think is over the ocean, because it's a big source of iodic acid, you are forming a lot more particles, which has, of course, we know that it forms a lot of particles, but it has not been implemented or looked at before. So what we think is, over the ocean, you have iodic acid, which is forming a lot more particles, more than what sulfuric acid is forming. And then these particles grow in size because of condensation and whatever aqueous phase chemistry and stuff. And by the time you reach the station, they're already in this larger Aitken mode sizes. And this we can also see from here when we compare it with the particle size distribution, just like it's divided now between the land and the sea. So if we just focus on ammonia, ABOA here over the land, and these values here, this 19 and this 81 is the fraction of time it spent. So 81% of the time the air masses was over the air mass was over the ocean, the sea, and just 19% of the time it was over land. And as you can see, over the sea, this iodic acid ammonia, the base case, we form more smaller particles in the medium particle size distribution. And then, of course, by the time they come on land, they just grow. You have some methyl iodide which is being transported. The lifetime is also kind of longer. So you will have some iodic acid also being formed over land, and then, cluster together to form more particles. But then it's not as important as it's over the ocean. Over the land, it's mostly just growing. So what about the vicinity of the station? Since the measurements suggest that it's sulfuric acid ammonia dominated, it's clear that the model is missing some gas phase species. And I think it's ammonia that we are missing, because the measurements after the campaign, they suggested that it should be around 3 to 30 ppb of ammonia, which is needed to explain this kind of formation rates. But what the model, when in simulations, we just find it's like around 0.1 ppt. So there is a lot of ammonia that we're missing. Even if we consider 3 ppt to be the threshold, we are missing it. We are missing like our ammonia concentrations are lower by a factor of 30 almost. So as you can see, this is the time before it arrives at the station, and this is ammonia. And it as a few hours before the station, just keeps on dropping. That's most likely because we do not have any sources of ammonia. There might be some bird colonies close by, some poo left behind by birds, which we cannot account for. So yeah, we have no way right now to actually estimate it. But there's also another factor that they have actually measured these three, like they have measured in this mass spec, they have measured sulfuric acid, ammonia, and iodic acid clusters at a lower concentration, but they still exist. So it's also possible that you have iodic acid, which is clustering with these different, different sulfuric acid, ammonia, or DMA, but we do not have them in the model, so we're kind of completely missing it as well. So there are some different possibilities why we are missing what's the smaller particles near the station. And since this is a modeling study, I would always like to end it by saying the known unknowns or the uncertainties in the model. So because when we did these simulations, we understood that there are some things which we do not know, absolutely do not know. There are some things which we are guessing. And that's also a call to the measurement department or the laboratory department, laboratory guys, to actually investigate. So our results use this iodic acid, iodous acid clustering, and iodous acid has been measured in the cloud chamber. But the formation of iodous acid is completely unknown. So we basically use the cloud data to get an estimate of the formation or the rate of this reaction I2O2, which forms HiO2. We use this kind of we use the cloud data to get an estimate of this. It's probably not right, but this is the best we can do right now, considering that this is supposed to be an important pathway, but we do not have the data, or we do not know how it is formed. And then again, there's a question of iodic acid diurnal pattern. As I guess some of you are aware, that the iodic acid diurnal pattern is opposite, like it peaks during the dawn. It like here in this figure, you can see this is the measured value. This is the diurnal profile. It peaks during the dawn, but during the day it decreases. Then again, it peaks in the evening. The model does not get this profile correctly. We get an opposite diurnal profile. But this is not a universal trend. It's been measured at ABOA. It's been measured at some Southern Ocean campaigns, but in different places in Antarctic, such as Marambio, they have a different profile. In Finland, in the Vario, in the northernmost part, they have a different profile. In Reunion Islands, they have different profiles. So it's not a universal profile. It's something happening there. So I mean, if these are some different profiles caused by different reasons, that also should be investigated. Of course, I guess there are a lot of smart people doing this investigations and stuff. So yeah. And the final thing is, of course, we rely a lot on emissions. And of course, there are a lot of uncertainties with emissions, such as these DMS emissions we get from ECARD. Some new results suggest that this DMS emissions from this, which is from which you can get from my card, is kind of overestimated by almost 40%. So yeah, there's a huge gap difference here. And of course, you have ammonia emissions and the fluxes of ammonia from the sea and whatnot. So yeah, there are a lot of uncertainties in these results and also in this, but yeah, this is the best we can do with what we have at the moment. So to conclude this particular paper, I would say that at least our hypothesis is that over the open ocean, even if iodic acid, even if you do not get the diurnal profile correctly or not, we still think that iodic acid can cluster with sulfuric acid. And this has also been shown in the last cloud paper where they looked at iodic acid and sulfuric acid ratios, and they suggest that even if it's a ratio of sulfuric acid to iodic acid of 0.1 or something, or 10, you can still form a lot of clusters between these two. So iodic acid can still cluster with other species, can form particles, and you have more particles where on which there can be more condensation of sulfuric acid or MSA being formed in the aqueous phase, and then these grow over time, and by the time you reach the station, you can get a better representation of these, maybe better than what we're getting right now. Yeah, so to conclude from the work that I've done in the polar regions now, we think that the aqueous phase reactions and in-cloud processes are very important to actually represent the realistic growth of particles, especially when it comes to size distribution, also the gas phase concentrations in these marine coastal sites. And iodic acid also should be, we should also think about including iodic acid maybe in the bigger models as well, because iodic acid in combination with bases, either DMA or ammonia or maybe some other base, can play a substantial role in the secondary reserve formation in the Southern Ocean. Yes, yeah, thank you. I hope I didn't go over time too much.
All right, thank you very much, Carlton. I think you were perfect on time, so no worries there.
Yeah.
Very nice presentation. I'll start us off with a question, and you have it right here on the slide about the aqueous phase reactions and cloud processing for MSA. I was wondering if you could quantify this, or if you tried to quantify this, given the kind of the relative contributions between aqueous phase processing and gas phase condensation for a particular MSA. Could you quantify the importance of each of these processes?
I did not quantify. I can go back to this one figure here. This is this here on this figure here. Can you see this? So this MSA here is only via condensation. So it's, I mean, compared to this, it's of course a very small amount. I don't remember the number on the top of my head, but the paper for this DMS chemistry scheme by Robin, they have quantified these values. I can't remember the number, but if you actually go through this paper, I think you can find the numbers, because they have compared it with this chamber measurements, and they have quantified how much of it is from the gas phase and how much of it is from the particle phase.
Okay, thank you. I'll go back and reread Robin's paper. Okay, and then we have a question from Lorenz in the chat about, I believe it was on your very last slide, where the known unknowns. He asked, should vertical mixing not be listed here as a feature, or is this still something that's a work in progress?
The vertical mixing, I think, yeah, it should be, but I think based on the kind of parameterizations we use, and that's the parameterization that's already been used in a lot of these MF models, I think we can reliably trust them a bit, I guess. No?
I just joined you because, I mean, thanks first of all for a nice presentation. I really appreciate it. And I see that you are dealing with a lot of uncertainties here on the chemistry, the sources, the things. But I think the vertical mixing is there, the essential component there that links all this to, like with the ammonia, having the source goes, but then also what is the fate of the ammonia during transport? Is it somehow arriving there in the free troposphere, or is it in the inversion layer, how much is being removed at the surface. So that's why I think that at some point the vertical mixing be a crucial connecting term here. I was wondering to what extent you are able to, for example, analyze to some detail the process tendency so that you can evaluate what is the role of the chemical production destruction, the heterogeneous versus the gas phase, versus then, for example, your assumptions on mixing and also maybe, for example, surface removal, any deposition at the surface. Because then you can maybe evaluate, okay, we can show that it's mostly the chemical uncertainty that we have to trigger down here.
Can you repeat the last part again, because there was a bit of a static in your
Yeah, I was wondering to what extent in your system that you can, for example, do any kind of process tendency analysis. You have the tendencies of what is the role of chemical cycling versus, for example, how much are the concentrations affected by the the, the mixing versus the chemistry versus, for example, deposition, so that you can really demonstrate it's mostly the chemical terms that are determining the variability in the concentrations, for example. So a tendency analysis.
Okay, yeah. I don't think we have actually performed a tendency analysis explicitly looking at vertical mixing or deposition as well, but yeah, probably it could be done for some of these, because we just focused on right now this chemical species and how the loss terms of these chemical species in the chemical reactions, but not really like the physical processes of wet deposition or dry deposition of like gases or the particles when they're lost.
Thank you.
Okay, then we have a question in the chat from Lauren Zamora. Could you design an aircraft experiment to test your important questions? Do you have any ideas? She adds, we are heading out to North Greenland later this summer for a second deployment of some NASA aircraft with aerosol cloud interactions, one of the main topics of interest. I don't think we can measure iodine containing particles though. Lauren, if you want to unmute yourself and add anything, if I didn't get your question right, feel free to do so.
Yeah, no, that was it. Just curious, if you had the opportunity to, if you've thought about that at all, we're going out there anyways. So if you have ideas about, some ways that we can test some of your hypotheses, that would be of interest. If the situation arises that kind of information could be collected, it's something we could keep in mind. So I was just curious if you thought of that before.
Yeah, so one thing that would always stuck us, because at least in I don't know about Greenland, but in the Antarctic region, they always say that it's probably the downdraft from the free troposphere which is actually impacting a lot of these compounds. So you have a lot of precursors which are coming in through the free troposphere. So it would be nice if you can actually get a closure, or at least see if this. I mean, I think there have been some measurements also in the southern hemisphere, ship measurements, where they have actually, I'm not sure if they have used any UAVs or something to look at MS in the free troposphere, and they have actually seen that MSA is being downdrafted from the free troposphere. So maybe it would be good to know if there's like how much of precursors are coming in from there, how much we are missing here, because all our emissions are from the ground base and nothing is coming up from there. So maybe we could have like as a boundary condition or something to see, or to get closure in our models in some way.
Do you think that a similar mechanism takes place in the Arctic as in the Antarctic for the free tropospheric inputs?
Sure, because I think at Zeppelin at least it should take place. I mean, Zeppelin, I mean, of course you have, I mean, the boundary layer at Zeppelin is kind of shallow. So I'm sure that if you have some emissions few days upwind, you will definitely have, you can definitely see that when you are at Zeppelin, or, when you're having this shallow boundary layer. So I'm sure you can actually see that in these Arctic as well.
Okay, thank you.
Oh yeah, this is a very interesting topic, Carlton. I definitely agree. In the southern hemisphere, these katabatic winds coming down, and I've often observed this too in the Arctic, frontal passages emitting or causing a lot of turbulent mixing, and then a lot of this DMS gets lofted into the free troposphere where there's more sunlight and less particles, so it gets oxidized up there. So that'd be very interesting to see if they can detect some of this with
Yeah.
their aircraft and their vertical measurements.
Yeah, sure. That's right.
Feel free, anyone, to raise your hand or post a question in the chat if you have one. Carlton, I have another question. You've shown a lot of nice work here from the Arctic and Antarctic. So what are your next modeling efforts going to focus on? The same topic, or moving to a different environment, or addressing a different question?
Oh, yeah. So right now I'm actually modeling, doing some model simulations for the Mosaic campaign.
Okay. Yeah.
It's a very interesting campaign because during different periods you have different precursor gases like MSA peaking at some point, and there's iodic acid peaking at some other point. So it'd be interesting to actually test if there are these, if we have these different like clustering species, how will they contribute to secondary aerosol formation?
Mm-hmm.
You have this MSA clustering with sulfuric acid and ammonia. Was it actually important, or is it just sulfuric acid ammonia when even though MSA peaks? Because I think even with Lisa Beck and her paper, they did suggest that MSA does contribute to, or also a lot of people actually suggest that MSA contributes to clustering, but we are not yet sure, or there have not been any observations. So we want to see it with the model if it actually does, and does it agree with the measurements at the mosaic time? Because you can clearly see from the mosaic data that you have different, like iodic acid is actually dominating at one point. I think it was in early spring and in September, but then you have MSA also kind of peaking in May, June, so, and the summer months. So I want to actually see if we can actually model these reliably, or is it only sulfuric acid ammonia, even though you have these different precursors as well. It's an ongoing work, so I haven't shown any results at the moment.
No, yeah, that's very interesting. I've seen a lot of theoretical quantum mechanical studies that do suggest MSA like this in the clustering. But you're right, I have not seen any measurements. Are you going to include MoCA in this comparison too, or just Mosaic?
Sorry, which one?
Are you going to include the MoCA campaign too?
No, it's just the mosaic for now.
Oh, okay. I was just thinking about Andrea Baccarini's nice iodine paper. They have some nice
Yeah,
measurements from MoCA too.
Yeah. Well, I haven't thought about including that, but it's because the mosaic data is also like, it's kind of huge for now. It's like a 1 year data set. So
And then in the chat, Lorenz adds comments on the very nice mini boundary layer and free tropospheric meteorological measurements that can help you validate your model against observations for Mosaic.
can I see the chat as well? Okay. Yeah, sure. I still have to look into all the data that the mosaic has. At the moment, I just have this particle and some gas phase data. So I'm actually also looking for more data sets to validate our model with as well. Yeah, that'd be great.
There's a lot.
Yeah. Maybe I can shortly comment on that. We have been doing a lot of work with 1D models, like what you're showing, to evaluate, for example, some of the mosaic data on the composition of ozone on other species. And I mean, that's what I like so much about the mosaic. It has all these observations that you can also then really first show, okay, do we get the meteorology right? Do we get the boundary layer height right? The mixing somehow? And I think that's key for if you want to evaluate all these detailed chemical processes. And but that's where really mosaic has been outstanding. We have all this detailed information about the vertical structure of the atmosphere. So
Yeah. Thanks.
if at some point you need some help with one of those steps on evaluating these 1D models, let us know, and we'll be keen to help.
Yeah. And then
Yeah.
you should sure to send you a message then.
Okay. Good luck.
Thanks.
Any more questions, comments for Carlton? Okay, so I mean, if there's any more questions, feel free to shoot Carlton an email or speak up right now. We don't have a next Catch Science seminar scheduled, so if anyone has any suggestions or anyone they know would like to show some cool, interesting results about the cryosphere or polar regions or alpine regions, you're very welcome to shoot me an email, or Hélène Agneau or Kwanzi Chen or Duwang John. Our emails are on the Catch Science seminar or Catch Science website. We're always inviting new speakers and would like to see interesting results. So if you know anyone or have any results yourself that would be good for a seminar, please reach out to us. Other than that, I would like to thank everyone who attended today, and thank you for some very nice questions and discussions. And a special thanks to Carlton for giving this very nice presentation today. Thank you very much.
Thank you. Thanks for this opportunity. Thanks.
All right, and then with that, I wish everyone a very nice day, and we'll see you next time.
See you.
Thank you.